Good afternoon. It is my great pleasure to be here today. My name is Pavel Gepner and I'm the senior system engineer, and I'm going to introduce Graphcore to you and talk about how AI meets HPC in scientific computing. Let's start with the agenda. Agenda for today looks as follows. We will start with the very short introduction of Graphcore, then we will go to the details of IPU architecture, then I will introduce you to our IPU pod system, then we will have the short introduction to our software Poplar SDK, then I will talk about the acceleration of the scientific application and enabling heterogeneity of AI and HPC, and finally, we will talk about the hybridization of the HPC and IA system. So a little bit about the Graphcore history. Graphcore is the British company with the headquarters in Bristol. Fundamentally, Graphcore develops processors, software, and computer system specifically designed for the AI and machine learning workloads. We provide the hardware as the IPU processor and the software as the Poplar software stack with development tools as part of the complete solution to enable innovators to solve current and the future machine learning problem. On the platform side, the first generation of IPU was implemented on the PCI card, but today our second generation of IPU processor has been delivered in the IPU pod rack scale products, which provide scalable solution which can ramp to the thousandth of the system to the supercomputing scale out, and I will be talking about this in the later of this talk. Let's start with the IPU details. Today, computationally intensive programming runs on the dense data, applying no algorithms, producing precise answer. We know this very well from the HPC world. In machine learning world, we are dealing with the completely new compute workloads based on the 6 fundamental principles. Massive parallelism, tens of millions of the parameters and connections needs to be executed simultaneously. Sparsity of the data. Not all parameters connected to everything else, and problems are very high dimensional. We need a mechanism which can go out and capture the data, get it together for the computation, and then scatter it back into the memory structure. Compute for the machine learning is low precision. We are not using floating point 64-bit as we know from the HPC. It is a group of all those small precision operations that makes the high precision outputs. There can be a lot of reuse in the model parameters when they is loaded to the memory for convolution or the recurrence, for example. Fundamentally, all those graphs are static. Like in the brain, we don't need to rewire the neurons when we are dealing with the new task. Taking advantage of this static nature of the graph, we can build the tools which can map complex graph structure and put them to the complex processor architecture. And finally, entropy or noise. Machine learning benefits from the injected noise. So dropout is an example. We need to find a cheap way to generate the noise. So if we will find a way to leverage all those into the processor, we should see the major performance efficiency improvement. At Graphcore, we have been able to work with many of the leading innovators in the machine learning. They have all told us that today's CPU, specially designed for the multimedia and the typical office application, and GPUs created for the graphics are holding them back. What they need is a new type of the processor that can efficiently support much more complex knowledge models, and this is why we have created Intelligent Processor Unit, the IPU. IPU is built from the ground up to meet those innovators' needs and help them make the new breakthrough in the machine learning intelligence. As we have already discussed, today's parallel machines are inflexible. They operated on the long data structure using the wide vector execution units, where all the units perform the same instruction at every step of the program. Using the Flynn's taxonomy, we can classify them as the SIMD category. They are good for the dense data structure, but completely inflexible for the sparse data. This classification fits to most of the modern CPU and the GPUs. The second aspect we need to take into consideration is memory compromise. Fundamentally, the energy cost to move the data around our system, plus some physical packaging constraint, is what limits how much bandwidth we can deliver with the fixed power envelope. This is some kind of the trade-off between the locality, how close we position our memory to the compute elements, and volume, how much memory we need. If we look at the typical DDR technology today, we need something around the 320 picojoule to move the byte of data from the memory into the processor core. With fixed power budget of 45 watts, we can there get something around 140 gigabytes per second memory bandwidth. Looking at the state-of-art external memory subsystem like HBM2 embedded with the CPU package using the silicon interposer, the energy per byte drops to the 64 picojoule per byte, meaning we can get something around 700 gigabytes per second at 45 watts envelope. An impressive 5 times improvement. Looking at the shared memory SRAM on the chip, we can get to the something like a 4.5 terabytes per second at the 45 watts. This is very, very nice, but still the 10 picojoule per byte. However, if we really want to maximize our memory bandwidth, we need to distribute our memory to all the devices to the local, very close to compute elements. This can drive the energy cost to the 1 picojoule per byte, delivering the huge 45 terabytes per second in our 45 power envelope. So how it is the IPU different? It is in the two key aspects, the level of parallelism and how it maximizes the memory access. In the case of the parallelism, as mentioned before, the CPU is a processor that was designed for the scalar processing and running general purpose application. They typically have a low number of cores and the level of parallelism is not that impressive. The GPU was designed for the graphic processor utilization using the SIMD architecture, which requires putting as much data as possible into the vector to make the most efficiently use of those instructions. So it is designed to work with the large blocks of dense data. The IPU, however, is the massively parallel media architecture. In the Flynn's taxonomy, we can classify this as the multiply instruction, multiply data. It can also be described as having a fine-grained architecture which is needed to address the efficiency of the AI models. And now look at the memory access. It really comes down to where the model and associated data are. The nature of the AI compute is massive number of the matrix multiplication operation and then exchange of data or weights. This is the very memory intensive activity, so the performance is heavily influenced by the memory bandwidth. In the case of the CPU, memory is typically out of the chip, as we discussed on the previous slide. In the case of the GPU, using the high bandwidth memory like HBM or any other sophisticated type of the memory in the conjunction with the shared SRAM can give us the performance benefits around 5x. However, if we really want to maximize the memory bandwidth, we need to distribute a large amount of memory right next to the compute part. Essentially, during the architecting of our products, we were thinking how effectively use of the massive parallel architecture and efficiently utilize it via easy of use software. And HPC brought the solution for us. In the 1980s, Valiant proposed the bulk synchronous parallel model as the parallel computing abstraction scheme that facilitates the expansion of the architecture algorithm. It's, in other words, something like a parallel version of the von Neumann model. We implemented the BSP in our hardware and made our software be ready for effective use of thousands of the independent threads. Our popular software is co-designed with our hardware and natively supports computational graph. This development of software and hardware together approach provides unique speed and flexibility for IPU performance increase. Let me use Steve Jobs' sentence. If you are really serious about building the hardware, you better be serious about building your own software. We have utilized both synchronous parallel model, as I mentioned before. This bridging model breaks compute down into the phases. Full parallel independent compute, where the tens of thousands compute threads all operating in parallel, each with all own data, they need to be held locally. They all complete their compute work at the same time. when our process have finished, the next phase is appearing, synchronization. This ensures that there are no data connections, races, deadlocks, or live locks. There, then the next phase follows, data exchange, where data is moved and copied to where it will be needed for the next phase of the parallel computing. The IPU processor has been designed to effectively implement this BSP model and includes hardware features that optimize power and performance. Let's look closer to the second generation Colossus M Mark II IPU processor, commercially named as the GC200, with the 59 billion transistor built using the TSMC 7 nanometers FinFET technology. Graphcore has once again built the world's most complex processor. Each GC200 processor has nearly 1,500 processor cores and runs nearly 9,000 independent parallel program threads, with proven multiply instruction, multiply data processor architecture. Inside the processor, we have been able to fit 900 megabytes of ultra high speed RAM that runs at the full speed of the machine. Not only we have the 250 teraflops of the AI floating point capability, but we also support much more IEEE float 32-bit compute than any other processor. This is the floor plan of the Mark II IPO processor, GC200. Key difference and improvements from the Mark I include the new number of the 10% increase in terms of the processor tiles. This now means that 8,832 independent processor threads can run on the IPU. Perhaps the biggest news is the massive upgrade in the amount of the in-processor memory, from the 300 megabytes to 900 megabytes. That is almost 1 gig of memory available to each IPU processor, making that data available and super fast bandwidth processor able to achieve 47 terabytes per second. And Mark II retains with the high-speed IPU link connectivity to enable connectivity between the IPUs, so the multi-IPU can scale and achieve seamlessly managed by the popular software architecture. Second generation Colossus Mark II IPU processor is the foundation of the pod system. IPU M2000 is the 1U 19-inch accelerating server appliance and is our IPU pods building blocks basic component. The M2000 IPU machine features 4-cylinder IPU engine with the 4R GC200 Mark II Colossus II IPU processor combined with the advanced airflow cooling system. This IPU engine is combined with the IPU fabric chip, allowing multiply IPU M2000 to be added in the rack and to be connected together to build the large IPU pods. And all of this supported with the exchange memory system and be able to provide around the 1 petaflops IPU compute power. Let's take a closer look at the M2000. This is the architectural block diagram showing the 4 GC200 Mark II IPUs. Now a special note is the massive on-chip memory allocation, exchange memory for the streaming into the IPU. We see the exchange memory sitting at the top of this diagram. They keep the IPUs always supplied with the parameters, models, data, weights, and any updates, etc. The IPU gateway, which we can see on the middle of this diagram, is the SoC. It's a very capable device and features the ARM Cortex quad-core processor. SoC is the Linux machine and is what gives the IPU its ability to run completely anonymously in appliance mode, for example. Of course, another major role of the SoC is manage the very high-performance IPU fabric links that communicate in the latter direction on the M2000 in the IPU pods configuration. It also helps manage the whole board management to maintaining very close view on the power, temperature, failures, etc. And does this together with the board management controller on the motherboard. This information communicates back to the management software using OpenBMC standard and the Redfish. The networking is compiled in the compile time. This means all the communication paths and events are known ahead of time and can be planned for the efficiently as practically eliminating memory access contamination, and delays. This is our Graphcore IPO scale-up story. The core building blocks of IPO M2000 is our Mark II processor, the GC2000. At launch, it was by far the world's most advanced processor chip, putting more than 50 billion transistors and provide 25 teraflops of mixed precision compute power. Our IPU machine, the IPU M2000, is our building blocks for the scale-out IPU machine intelligence system. It contains 4 Colossus Mark II and connect them via IPU link. This provides 1 petaflops of AI compute with the integrated streaming memory. It is a flexible modular design, scalable from 1 to the thousands of units. Up to 60 of those M2000 can stack together in the industrially type of the rack, and this is what we are calling IPU Pod 64. This provides the core building blocks for the future scale-out into exascale domain, allowing potentially up to 64,000 of IPU to be supported, delivering up to 60 exaflop of the AI compute. This allows customer to start small with the single M2000 or the IPU Pod 64 and scale out up to the 1,000. This is necessarily for the very huge workloads in the multi-trillion parameter model era. Let's talk about our software. Let me explain how our popular software pulls all this capability together and makes it extremely easy to use. The Poplar SDK provides the capable software stack which implements our graph toolchain. Poplar allows innovators to use the existing high-level machine learning frameworks such as TensorFlow, Onyx, and PyTorch, so they can easily target the existing machine learning model to the IPU, even if they were originally developed for the CPU or the GPU. This enables maximum portability and easy of use for out-of-the-box performance. However, for those that are waiting for squeeze maximum performance out of the IPU, it is possible to develop models at much lower level, much closer to the hardware. Let's talk about the IPO Advantage. Here are the few examples in the 3 of the vertical markets. First is the example in the healthcare. Some of the work done by Microsoft AI Advanced Architecture Lab. The Microsoft researchers were able to easy port their model to the IPU with the Poplar software tools, and out of the box they found a 12-time gain in the throughput and the faster time to train. The next example is from the internet market with the French search engine company Quant. They wanted to move to ResNext versus the ResNet to increase the accuracy of the object recognition. However, they also need to meet the 5 millisecond latency requirements for the completing the inference part. The IPU provided 24 times speed up and 7 times higher throughput, easily meeting the 5 milliseconds real-time requirement. The third example shown here from the finance. In the finance, they look for the new probabilistic model that improve the accuracy of the alpha estimation. However, these kinds of the models do not fit well to the SIMD type of the architecture, so GPU is not the alternative. In this case, Cremont found the 26 speed up with the IPU, enabling them to develop more competitive prediction model. These are all the examples from our first generation of IPU Mark I versus NVIDIA V100. But we are doing much better with Mark II and the IPU pods. The IPU is being used across many areas of research in industries and academic institutions around the world. Here we see some examples of published research papers and press articles. For example, the University of Bristol benefit from the IPU highly parallel compute in their research on CERN Large Hadron Collider experiment with the 5.4 times faster performance to their gene application. In another example, researched at the Université de Paris has published a paper about the use of the Graphcore IPU to accelerate the neural networks training for the cosmology application. We can find more recent results visiting the URL you can see on the bottom of the slide. At Graphcore, we developed the IPU so the innovators can create the next breakthrough in the machine learning. It is completely new hardware architecture specifically designed for the workloads of AI and machine learning, which is especially beneficial for the advanced high accuracy model that in the future will be where the machine learning is heading towards. We are excited about what we can achieve in the AI and machine learning, but we are looking to the HPC segment as well to see how our technology can enable AI and the HP heterogeneity. Uh, our IPO architecture is specifically developed for the AI type of workloads and doesn't fit typical HPC application in the pure form. Nevertheless, IPU can improve and extend the HPC classical simulation via surrogate calculation model. If we replace the classical simulation solver using machine learning model, we can achieve the great results. This approach uses the data generated during the HPC simulation to train the machine learning replacement model, which then predict responses for the new iteration of the experiment much faster. Let's take an example from the CFD. In the data generation phase, we use the classical HPC solver to generate the data. Then they use generated data to build the model and train it. When the new iteration will come, we'll use our train already model to predict the result. If we look on the diagram in the bottom of the slide, we see that the simulation time can be reduced significantly. Modeling experiment phase will stay in the both scenarios the same, but simulation time can be accelerated by implemented AI module. Many researchers already use such approach, and in many areas, the integration of the AI acceleration model with HPC simulation brings great results. Today, we see spectacular results in the area of high energy physics, computational fluid dynamics simulation, partial differential equation, protein folding, Monte Carlo simulation, weather research and forecasting, oil and gas exploration simulation, and many others. But to make this approach successful, we need the new type of the system. This hybridization of HPC and AI is happening today. As we see, the single monolithic system are not able to satisfy both worlds, HPC and machine learning. For typical HPC workloads, we have the system based on the hundreds or thousands of the CPU and the GPUs. And they are also a hybrid system in some way. But for the AI workloads, we can use the pod. It is pod 16, 64, 512, or we can go to the hundreds of racks of 64,000 of IPUs if are needed. But for the heterogeneous type of the workloads, we require a new hybrid system compiling benefits from the both worlds. And this is the way how we accelerate and achieve sustained exascale performance. To summarize, the IPU and the IPU post system with our popular software are our solution for a scale-out AI compute. The integrated network and scalable architecture enable us to start small and go very, very big. The IPU is being used across many areas for research in AI and machine learning. And finally, we believe that the enabling heterogeneity of AI and HPC can be the new way of performance acceleration for the exascale system era. This is all from me today. Thank you very much for taking the time to listen to this presentation. We have a lot of more information on our website. Feel free to contact us via our websites or email addresses or follow us on the Twitter. Thanks very much.